Understand. All right, today I'm here on behalf of Hongbo Shao, who was a postdoc in our group at Geosciences group at Pacific Northwest National Laboratory. I want to recognize the contribution of Amanda, who is sitting somewhere here in the auditorium. She presented a poster on some different aspects of the work that we are doing. I want to recognize the contribution of Mark Bowden, coming from AMSL, that is part of PNNL, and Chris Brown, who is the lead, technical lead for this project at PNNL. The data that I will be presenting today are part of the efforts within the NRAP. You have heard by now many talks about NRAP, which is sponsored by the Fossil Energy Office of the Department of Energy. And Pacific Northwest is part of the National Laboratory Systems of the Department of Energy. All right, so carbon storage and the overall concept. Geological carbon sequestration is considered a feasible option for controlling increasing atmospheric, it's fine, CO2 concentration. As you are well aware, the concentration of the CO2 in the atmosphere is currently over 400 parts per million. So many scientists are now considering many options, you know, what to do with that increase in the concentration. And carbon capture and storage will contribute 14% of the total emissions reduction through 2050. One of the ways that is considered right now is the injection of the CO2 deep in the subsurface. As part of that effort, the potential risk associated with the leakage of the CO2 and the brine from the storage reservoir must be assessed. And that is why we actually started a program of research 2 to 3 years ago, and trying to do a series of experiments to try to evaluate the potential risks associated with the leakage of the CO2 from the deep reservoirs. Of course, we are interested in the effect on the groundwater and the aquifers, so basically my talk today will be focused on that part of the subsurface. Another aspect is that the leaking CO2 saturated reservoir brine may in some cases contain contaminants, so basically one of the aspects of the research work, of the experimental work that we are doing at PNNL deals exactly with that effect. So we will try to understand what is the effect of the contaminants that are traveling up from the deep subsurface reservoirs, and what will be their effect on the quality of the groundwater. Wrong one. The conventional thinking is the following. I mean, it's a simple reaction, as everybody knows by now, because there have been so many talks about it. The CO2 gas actually dissolves in water, forms the carbonic acid, and the carbonic acid dissociates and produces some protons. The problem is that what happens with these protons? And of course, the effect is in the decrease in the pH. Now, this is kind of a simple reaction, but you know, everybody knows that the pH is one of the major geochemical variables in the subsurface. So basically, if you change the pH, you are changing the rate and extent of many other possible reactions that might simultaneously or sequentially occur in the subsurface. And that is the reason why we are very keen to looking at these changes in the subsurface. Some of the reactions actually that might be triggered as a result of a change in pH is the exchange reactions that were part of some of the talks today. And in addition to that is the enhanced mineral weathering or the dissolution. So as it was pointed out by the previous speaker, and especially by the question that followed, there are many minerals, and especially calcite, that actually can host many different contaminants. And as a result of the dissolution of calcite, some of those contaminants that are part of the crystal structure of calcite might be released in the aqueous phase, contaminating the groundwater. This is one important step that needs to be considered. So, what we did a series of batch and column experiments that were conducted at the room temperature and under atmospheric pressure conditions. The batch system simulates sudden and fast release of the CO2, while the column experiments simulate a slow, gradual leakage. There are many things here, many details, and I don't have really time to go over these details. However, we have recently submitted a series of papers that will be published, hopefully, recently. Will be published in the future. So if you are really interested in details, experimental details, or if you are really interested in the results that we are generating as part of this work, please stop by and talk to me after my talk. Sediment samples that are part of the talk that I will be presenting today are coming from the High Plains Aquifer, and this talk actually connects very well with the one presented by the Susan Carroll group, because it's an attempt to measure and to evaluate experimentally some of the parameters that hopefully might be used in the modeling that Susan Carroll and the others are doing as part of this effort. I will try to very quickly go over some of the data that we collected from some batch experiments. So the experiments were done with two sediments here, the CNG60 and CNG110. The main difference is that the mineralogy is kind of similar in both these two, but in 110 we had some appreciable amount of calcite, or let's say detectable amount of calcite, and we were not able to detect any calcite presence in the CNG60. This is important because when you expose the sediments to the CO2 stream, what would happen is that in the sediment that does not have any calcite, the pH, the equilibrium pH that you get is around 5, while the equilibrium pH that you get in the case where some calcite is present is a little bit higher. And of course, the pH is actually buffered by calcite dissolution. My focus today is on arsenic mobility and on cadmium. However, we have measured many elements. We have measured all elements that are released in the aqueous phase as a result of those dissolution reactions. So if you are interested, again, I can provide data on those measurements as well. In terms of the arsenic, we discovered that some of the arsenic was released in the aqueous phase as a result of exposure of the sediments to the CO2 stream. However, the amount of arsenic that was released is kind of small and is very similar to the 10 micrograms per liter that is the EPA MCL for arsenic. Now, we conducted some experiments that were done with synthetic groundwater or with groundwater that was spiked with arsenic. The idea here is, again, to actually study what would happen with the arsenic if it potentially comes together with the CO2 or brine from the deep subsurface storage reservoirs to the aquifer. And surprisingly enough, we saw that the concentration of arsenic from 114 that was in the initial spike went down, and it actually stabilized at around 20. So basically the sediment reacted positively to the increase in the arsenic and actually sorbed some of the arsenic that we spiked, we injected in the initial solution. There are differences in terms of the behavior of the two different sediments, and I don't have time to go into details and what are these differences and why there are these differences, but again, if you are interested, you just stop by and we can discuss those. Cadmium behaves the same. Again, the spike concentration of the cadmium was around 40 parts per billion. We see that in our experiment, most of the cadmium was absorbed actually by the sediment. So we don't see any CO2 enhanced release of the cadmium, or we don't see any negative effect of the CO2 exposure of the sediments. One point that I want to make clear during this presentation is that we started doing some work modeling the work, and for that we asked the help of the Liang Zhang from LBNL. And I wanted to recognize his effort because they are very well appreciated. Jens actually presented some data from the model that Liang developed for a totally different site. This is the EPRI site. And what Liang did here, he used the same conceptual model to apply that to a totally different site, that is the High Plains Aquifer. And I'm very glad to see that he was successful, in fitting the data that we generated in our PNNL laboratories, following exactly that conceptual model. So kudos to the modeling guys, you know, it's a great effort. And this is my major point here. There are many things to be discussed here, of course. The way that these two sediments behave, these are again sediments without any calcium, and this is the sediment that had appreciable amount of calcium. And these are results from the column experiments. And the column experiments, as you know, are conducted under solid solution ratio that is different, much different than what the solid solution ratio is in the batch experiments. So again, I don't have much time, but the take-home message here is that the modeling actually does a good job, taken from a different site, applied in our site. Of course, there are many aspects. You know, if you go to the arsenic behavior, for example, the model does a marvelous job. Following the changes in the arsenic concentration. It doesn't do much better job in the other sediment. And of course, this brings about another point that I want to make, that the importance of the site-specific behavior. So, of course, we can actually apply a model that is very well thought of, a conceptual model, but keep in mind that there are site-specific specifics that needs to be taken into account. I have 42 seconds, so.
With time for questions.
With time for questions. So I'm going to move to the conclusive remarks of this talk. The results demonstrated from this part of the experimental, from the experimental results that I presented, the results demonstrated that the CO2 gas would not release significant amount of contaminants found naturally in the sediments of the high plains. Even if CO2 leaked into the aquifer together with storage contaminants, the gas did not prevent these contaminants from being removed through reactions with the sediments. Calcite dissolution and calcium-driven cation exchange reactions were the major drivers for the concentration changes of major elements. There was some specific related to the barium behavior, but Liang's paper actually describes it in full, and I can provide you a copy of that if need be. And the pH-driven adsorption-desorption reaction led to a concentration increase in arsenic and lead. And also, results demonstrate the importance of the site-specific evaluation prior to CO2 concentration. Before I conclude, I would like to actually thank a lot the organizer of this session, because it was an extremely interesting session for me. Thank you again.
All right, we've got a minute or two for questions for the speaker. If there are no questions from the audience, I have a quick one about the batch experiments.
Mm-hmm.
I'm still a little confused. The unspiked, unarsenic spiked batch experiment showed some release of arsenic after exposure to CO2. But when CO2, brine, and a large arsenic spike were added, there was a decrease in arsenic concentrations.
Correct.
So what is the mechanism that you're proposing?
That is a great question. And thank you for bringing that. And I didn't have time to go through the other. The arsenic story happens to be a complicated one, because we did some column experiments with a synthetic groundwater which was spiked with arsenic. And we used arsenic 5 to spike the synthetic groundwater that is injected into the column. And we followed changes in the arsenic concentration in the effluent. And we did the speciation of that arsenic that was coming out of the effluent. And what we discovered was that most of the arsenic that was coming out was arsenic 3. So, the ternary complex, arsenic 5, arsenic 3, and calcite, is a pretty interesting complex, and has not been studied to the extent I wanted. I went back in the literature and I looked carefully to see what is going on. The thing that is going on right now, I think, that is the following. Arsenic 5 is able to absorb more easily to the minerals in the soil than arsenic 3. Now the question is that what is the source of arsenic 3? Is it something of a reduction reaction that is occurring during our experiments, or arsenic 3 is coming from the structure of some minerals that are dissolving during the experiments? I'm leaning towards the second one, and I think that's what is going on there. And that is why some of the data that I presented for the arsenic are not as simple to be interpreted.